Right, so here we go again. Parametric differentiation. This is hopefully be a nice video. We're going to do it as sort of an example alongside the theory. So anything in blue will be the specific example we're looking at. Anything in black is just generally true of parametric differentiation. So I think it's a helpful way to sort of think about things. So what we're going to do is we're going to just recall what it means to parameterize something. That just means we've got this extra variable t. So if you think about it like this, imagine you've got some point in space, we call that coordinate A, and the x value that it's at is some function of t, which can be confusing in itself. And the y value similarly is also a function of t. So what we're going to do is we're going to create a simple example. If we look at something like this is a simple parameterization. We'd say that the x value is equal to whatever t is, and then the y value is equal to t squared. So I encourage you to think about what shape we're going to get, but what I can actually show you is that's this point here, A, right? So let's sketch that out. At the moment, when t is 0, or t is 0, t squared is also 0, but as I start to move t around, we get this, right? And it graphs out this shape, right? Which I'm hoping you realize is a parabola, right? Y equals x squared. Okay, so that's sort of a simple parameterization of our of a simple of y equals x squared, right? So what we can do from here is we can think to ourselves, all right, what is the derivative of this? And I hope you've done enough differentiation at this stage. You would say that the derivative of x squared is 2x. So that should be our result, right? So how do we do it when it's parameterized? Well, this could be our question. Determine the gradient dy dx in terms of t. So I want to know what the derivative is in terms of t. So what we need to recall is the chain rule, okay? You might recall that the chain rule is dy dx equals dy dt multiplied by dt dx. And I'll put some links below to explain the chain rule in more detail, but that is a conclusion that we've come to previously. And what we're going to say is recall that dx over dt is 1 over dt dx. And again, we're treating this like a fraction. Dx over dt is the reciprocal of dt dx, okay? Just like 4 equals 1 over 1/4, that sort of idea. Okay, so you would agree, just maybe get a pen and pencil out if you're not sure, but I think you would agree that dy over dt divided by dx dt is just dy over dt multiplied by dt over dx. So I encourage you to sort of step that out if that's not super familiar to you, but that's just sort of working with fractions. Again, we're treating these like fractions. Okay, so what we can say in our specific example is, well, let's just apply this logic, all right? So if we take dy dt, all right, y is a function of t, so the derivative of y with respect to t is 2t. Okay, dt dx. Well, let's work out dx dt. The derivative of x with respect to t, well, x of t is equal to t, so the derivative of that is just 1. Okay, so dx dt is 1, so we take 1 over 1, which is just 1. Okay, and so we get 2t multiplied by 1, which is just 2t. Okay, and then what we can say is we can now graph that. We know what 2t is. That is a function of t, so we can graph that as well. So if I start moving t around now, this is the point B, you might notice. And it's not going up very high, but you get the idea. Let me make that a bit better. Yeah, so if we just sketch those out again, you get something like this, right? A is our original function, and then B is our derivative, which we've got in blue now. So yeah, pretty cool. Pretty fascinating result, I think, because we're going to need to use this result in other maths that we're doing. But, pretty handy that the derivative of a parameterized function is just the derivative of y over t with respect to t divided by the derivative of x with respect to t. So not at all obvious necessarily, but a very important conclusion for some of the other things that we're going to do later on. So hopefully you found that useful. And yeah, good luck with all your studies, and I'll see you soon.